Take the number 729. Dividing it by 9 seems like work, but adding its digits gives 7 plus 2 plus 9, which is 18. 18 is divisible by 9, so 729 is 2. This shortcut works for numbers with 10 digits, 1,000 digits, or 1,000,000 digits. It even survives when the digits are repeatedly collapsed to 1. Why should addition inside a number reveal division of the whole number? The answer is hidden in the way base 10 is built. This is symmetry. Let's find out why. First, watch the rule work before we explain it. Start with 729. Its digit sum is 18, and 18 reduces again to 9. The original number is 9 times 81. Try 4,617. Its digits total 18 again, and the number equals 9 times 513. Now change the final digit from 7 to 8. The digit sum becomes 19, which is not divisible by 9, and 4,618 leaves remainder 1 when divided by 9. The rule tracks not only divisibility, but the exact remainder. The test is simple. Add every decimal digit. If the result is still large, add its digits again. Continue until one digit remains. A final 9 means the original positive number is divisible by 9. A final digit from 1 through 8 gives its remainder after division by 9. 0 is the special final digit only when the starting number itself is 0. Positive multiples of 9 collapse to 9. This repeated one-digit result is called the digital root. A pattern appears if we list consecutive numbers. 8 has digital root 8. 9 has root 9. 10 returns to 1. 11 goes to 2, and the roots climb again until 18 returns to 9. The cycle repeats every 9 numbers. On a number line, numbers with the same digital root sit 9 units apart. This suggests that the rule is really about remainders, not about the visual shapes of the digits. To prove it, we must open a decimal number and inspect its place values. The remainder clock makes this cycle concrete. Place 0 through 8 around a circle. Adding 1 moves one step, adding 9 makes a complete turn and returns to the same point. 729 and 18 land together because their difference is 711, exactly 9 times 79. The digital root does not claim those numbers are equal. It says they occupy the same position after complete groups of 9 are removed. Every decimal digit is secretly multiplied by a power of 10. The written number 729 is not merely the symbols 7, 2, and 9 placed side by side. It means 7 times 100, plus 2 times 10, plus 9 times 1. Using powers, that is 7 times 10 squared, plus 2 times 10, plus 9. Every longer decimal number follows the same blueprint. Each digit multiplies a power of 10. The divisibility rule must therefore come from something special that powers of 10 do when divided by 9. Divide 10 by 9. It is one group of 9 with 1 left over. So 10 and 1 have the same remainder modulo 9. Write this as 10 is congruent to 1 mod 9. Square both sides conceptually. 100 is 10 times 10, so its remainder behaves like 1 times 1, still 1. 1000 also leaves 1, and every power of 10 does the same. In fact, 10 to the k equals a multiple of 9 plus 1 because 10 itself equals 9 plus 1. Now compare place value with the digit sum. 7 hundreds contributes 7 times a number whose remainder is 1, so it contributes remainder 7. 2 tens contributes remainder 2. 9 ones contributes remainder 0, since 9 is divisible by 9. The whole number therefore has the same remainder as 7 plus 2 plus 9. Place value weights hundreds and tens differently in ordinary size, but modulo 9 all those weights collapse to 1. Once every power of 10 becomes 1, only the digits remain. A block model shows the same collapse. 100 objects can be packed into 11 complete groups of 9 with 1 object left. 10 objects make 1 complete group with 1 left. 1 object is already the leftover. Replace every 100 block and 10 block by only its remainder tile. 7 hundreds leave 7 tiles, 2 tens leave 2, and 9 ones form a complete group. The surviving tiles count the digit sum modulo 9. Now build the argument for every decimal number at once. Write a general decimal number with digits a sub 0 through a sub k. Its value is a sub 0 plus a sub 1 times 10 plus a sub 2 times 10 squared, continuing through a sub k times 10 to the k. Modulo 9, replace every power of 10 by 1. The expression becomes a sub 0 plus a sub 1 plus a sub 2 through a sub k. Exactly the digit sum. Therefore, the original number and its digit sum always leave the same remainder after division by 9. There is also a proof without modular notation. Subtract the digit sum from the original number. For 729, subtract 7 plus 2 plus 9. Group by digits. 7 times 100 minus 7 plus 2 times 10 minus 2 plus 9 minus 9. This equals 7 times 99 plus 2 times 9. Every term contains a factor of 9, so the difference is divisible by 9. If two numbers differ by a multiple of 9, they must have the same remainder. Repeated digit sums are now justified. The first digit sum has the same remainder as the original number. Its digit sum has the same remainder again. Each arrow preserves the remainder, so the final one-digit result does too. For 987,654,321, the digits total 45, then 4 plus 5 gives 9. We never divided the enormous number, yet the proof guarantees that it is divisible by 9. The proof also explains familiar quick moves. You may erase any digit 9 because it contributes 0 modulo 9. You may erase digits that total 9, such as 2 and 7 or 4 and 5. In 987,654,321, pair 9 with nothing, 8 with 1, 7 with 2, 6 with 3, and 5 with 4. Every group disappears, leaving remainder 0 without performing the full sum. The rule can detect mistakes as well as divisibility. Before calculators, accountants used a method called casting out nines. To check an addition, reduce every input to its remainder modulo 9, add those small remainders, and compare the result with the digital root of the claimed total. For example, 286 plus 457 should equal 743. The first roots are 7 and 7, whose sum reduces to 5. The claimed answer also reduces to 5, so it passes the check. Large columns become tiny arithmetic. Now suppose the answer is mistyped as 734. Its digit sum is 14, reducing to 5, exactly like 743. The checksum does not notice because swapping two digits preserves their sum. It also misses any error that changes the result by a multiple of 9. Passing the test, therefore, does not prove an answer is correct. Failing proves something is wrong, but passing only says the arithmetic is consistent modulo 9. A checksum compresses information, and compression inevitably loses detail. The strengths are still useful. A single wrong digit usually changes the digit sum and is detected unless the change is 9. Adding or dropping a digit usually changes the remainder. Many arithmetic mistakes also alter it. Modern identification numbers use more carefully designed weighted checksums, but the principle is similar. Transform a long string into a small remainder that is easy to compare. The divisibility rule for 9 is therefore an elementary example of error-detecting mathematics. Measure the limitation precisely. A random wrong answer has one chance in 9 of sharing the correct remainder, so this simple check catches roughly 8/9 of unstructured errors. Transpositions are worse. Swapping decimal digits changes the number by a digit difference times a power of 10 difference, always a multiple of 9. Every transposition therefore survives. Weighted modern checksums deliberately vary the place weights, so that swapped neighboring symbols usually stop matching. Other divisibility rules come from other power patterns. The rule for 3 is immediate. 10 leaves remainder 1 when divided by 3 as well as 9. Therefore, every power of 10 becomes 1 modulo 3, and a number shares its remainder with its digit sum. 729 has digit sum 18, divisible by both 9 and 3. 412 has digit sum 7, so it is divisible by neither. The same construction works because both 3 and 9 divide 10 minus 1. 11 behaves differently. 10 leaves remainder negative 1 modulo 11 because 10 is 1 less than 11. Powers of 10 therefore alternate: 1, negative 1, 1, negative 1. A decimal number reduces not to the ordinary digit sum, but to an alternating sum of digits. For 5066, compute 6 minus 6 plus 0 minus 5, giving negative 5, so it is not divisible by 11. But for 5060, compute 0 minus 6 plus 0 minus 5, giving negative 11. That is divisible by 11, and 5060 equals 11 times 460. Why is there no equally simple digit sum rule for 7? Powers of 10 modulo 7 cycle through 3, 2, 6, 4, 5, 1 before repeating. The place values do not all collapse to 1 or merely alternate signs. A valid test can still be built, but its weights form a 6-step cycle, so the shortcut is less memorable. Divisibility rules are not magic tricks attached arbitrarily to numbers. Their shapes are determined by the remainder pattern of powers of the base. We can classify the easiest decimal tests by factoring numbers near 10. Divisors of 10 minus 1 inherit the ordinary digit sum, giving 3 and 9. Divisors of 10 plus 1 inherit the alternating sum, giving 11. Divisors of powers, such as 100 or 1000, allow digits to be grouped into blocks. That is why tests for 37, 99, and 1001 often use 2-digit or 3-digit chunks instead of individual digits. Change the number system, and the special divisor changes with it. In any base b, place values are powers of b. Modulo b minus 1, the base itself equals 1, so every power of b equals 1. Therefore, adding the digits tests divisibility by b minus 1. In base 8, digit sums test divisibility by 7. The octal number 351 has digit sum 9 in ordinary notation, which leaves remainder 2 modulo 7. Its decimal value is 233, also remainder 2. 9 is special in decimal only because 9 is 1 less than 10. Modulo b plus 1, the base equals negative 1, so powers alternate signs. That generalizes the 11 rule. In base 10, b plus 1 is 11. In base 8, the analogous alternating sum test detects divisibility by 9. The two famous decimal shortcuts are therefore mirror images. b minus 1 makes all place weights positive 1, while b plus 1 makes them alternate positive and negative 1. Both come directly from the algebra of place value. Return to 729. Its hundreds, tens, and ones look unequal because place value makes them 100, 10, and 1 times their digits. But division by 9 erases exactly that difference. Every power of 10 leaves 1. The number and 7 plus 2 plus 9 therefore carry the same remainder. 18 carries the same remainder, and 9 reveals divisibility. The shortcut works because base 10 is 1 more than 9. What looked like a coincidence among digits is really a structural shadow of the number system itself. The broad lesson is an algorithm for discovering rules. Choose a divisor, calculate the remainders of successive place values, and look for a short pattern. Constant ones produce a digit sum. Alternating signs produce an alternating sum. A longer repeating cycle produces repeating weights or digit blocks. This method replaces a collection of classroom tricks with one construction. Every useful rule is a compressed picture of how powers of the base travel around a remainder clock. A huge number can hide its size, but not its remainder. Thanks for watching. For more visual mathematics, subscribe to Symmetry.